Hello everyone, welcome to NPTEL's Introduction to Semiconductor Device course. I'm Om Maheshwari, and today we will discuss some questions that will help you in your assignment as well as your exams. This is the week 11 live section. So before we go to the questions, let us first look at a recap of the week 11 lecture. So I hope you have till now you have already gone through the lecture, but I'll quickly overview the lecture slides so that you get a recap. So the lecture starts with optical absorption. So this figure shows optically generated electron hole pair formation in semiconductor. So when some photon strikes on the semiconductor device, the electrons from valence band goes to the conduction band, leaving a hole behind. This is called as optical generation. And if we look at here, this next figure shows the photon intensity versus distance for two absorption coefficients. So So if we have a larger absorption coefficient, the uh, photon intensity uh, uh, degrades faster with time, whereas a smaller has a slower degradation. And this absorption coefficient is actually dependent on the parameter alpha. And that absorption coefficient is the parameter alpha, and it is dependent on lambda. It depends on the wavelength, inversely proportional to the wavelength. So if N0 is the initial number of, so what is intensity? So if N0 is the initial number of photons, this dN by dx uh, is what is the gradient of change in number of photons. And if dN by dx is equals to minus alpha times n. So n equals to N0 e to power alpha x, and I equals to I0 e to power minus alpha x. This is the transmitted intensity. So it just means if this intensity basically means like if this distance is in the x direction, like here, if your incident are 100 photons, how many are transmitted through the medium? So okay, so this here shows the optical absorption in the materials. So photon energy is 1.24 by lambda in micrometers. If lambda is 0.5 micrometer, energy is 2.48 electron volts. So we have discussed this many times in the code, direct and indirect band gap semiconductors. So optical absorption is actually difficult in indirect semiconductor because it needs change in momentum also, right? So first it needs to change the momentum, then it will absorb. So then it can emit something or absorb something. So direct band gap semiconductors, they are easier optical emission or absorption due to the delta K. There is no delta K here. So here if photon strikes, it will increase the energy, but then it will need to change its momentum to go to the conduction band value. The electron will need the change in momentum. So just an example, calculate the thickness of semiconductor that will absorb 90% of incident photon energy. So if alpha is 10 square per centimeter and 10 to the power 4 per centimeter at 500 nanometer. So I equals to I naught exponential of minus alpha times x. So 0.1 is exponential minus alpha times x. So x will be ln 0.1 by 10 square centimeter, which is alpha, right? In the same ways, if so, this will give you x is 0.023 centimeter. it will be the thickness of semiconductor. Whereas if alpha is very large, 10 to the power 4, you will get 2.3 micrometer, very smaller uh, x. Next is the generation of electron hole pairs. So calculate the generation rate of electron hole pairs given an incident intensity of photons. Consider gallium arsenide, temperature 300 Kelvin. Assume the photon intensity at a particular point is this, and the wavelength lambda. The intensity typical of sunlight is going to be typical of sunlight. Okay, so I is n number of photons per centimeter square into EHV. Right, so this n lambda is given by 0.05 watt. This is IV divided by 1.64 into 1.6 into 10 to the power minus 19. So this 1.64 is what? Energy E lambda. Uh, so this we got from 1.24 by lambda. This we have already seen. So this energy comes out to be 1.64 electron volts. And so by solving this, you get 2 to the power 17 photons per centimeter square per second. So number of absorbed photon is alpha times n lambda. So alpha is this much, 10 to the power 4 per centimeter into 2 into 10 to the power 17. This is photons per centimeter square. So 2 to the power 21 electron hole pairs are generated per centimeter cube. So this is about solar cells, LEDs, photon flux, energy of photon. Again, this 1.24 factor, 1.24 by lambda will be 1.24 by the energy in electron volt. This will be lambda. So when light is incident on p n junction, uh, in quasi-neutral region, no current. In deletion region, current flows in external circuit. So when light is incident on p n junction, so this is how the solar cell works. Solar cell works in a reverse bias. When light falls on it, uh, there is a potential generated so solar cell works like this. When light falls uh, on the depletion region, the potential is generated across the load. So this graph is solar cell generated power. This is the maximum power point. When the solar cell is shorted, the I total is IL, which is ISC. That is when potential is zero across the solar cell. That this current is ISC. And in open circuit, when it is open circuit, this VOC case. So VOC is QT by Q ln 1 plus IL by IS. So this V into I actually give you the power, right? So with the power diagram, this at this point we have somewhere we have maximum power point. Say we want to operate it. So the maximum power point we can calculate by dp by dv is 0. At maximum point, this is the I total minus IL plus IS exponential 2v by kt minus 1. This is IL. So you just put the derivative and find that. Uh, okay. Efficiency and bandwidth. The maximum theoretical efficiency of single solar cell is 33.7% at a bandwidth of 1.34 electron volts. Silicon has less favorable bandgap of 1.12, which with theoretical maximum efficiency of 32% only. And modern commercial solar cells have efficiency of 24% due to reflection loss, metal wire contacts, emission resistance, etc. So this is about photovoltaics now. So if you have some semiconductor and some current is flowing through it, if you shine some light, there will be generation of additional carriers. If it's N-type, so you can detect the P-type carriers also there because N-type cable will be small. So your J naught is the equilibrium current. JL will be the current due to light that you can detect. And JL is given by this formulation. So a good photodirector has small thickness, large tau p, and J is proportional to tau p by L. Tau p is the lifetime of the generated carriers. So in this equation, if you put some values, you will get JL is around 20.2 ampere per centimeter square. So photovoltaic detectors. There is a photoconductor detector and photovoltaic detectors. Uh, Photovoltaic detectors have an NP junction, which is reverse bias. So here JL is given by QWLN plus LP times GL. This is an estimation where W is the depletion rate, LN is the biotic area lifetime of electrons in P-type semiconductor, and LP is the biotic area lifetime of those in P-type semiconductor and N-type semiconductor. And this gives you around milliampere per centimeter square of current. So to improve the response of the photodetectors, you can use PIN diode. Basically, we are increasing this depletion with W. So if you use an PIN diode, this whole I will be depleted. So this will give you more current, light current, or more depletion with you have more electron hole pair generation, more uh, light current will be get. Okay, so I think let us go to the questions now. Okay, so all right, so in this week we are dealing with the optoelectronic devices of daily life, direct and indirect band gaps, optical absorption, and other things. So let's see, this is the first question. Please attempt it, then we will solve it together. Okay, so the question asks two beams of light with same intensity, initial intensity I naught, pass through two different materials with absorption coefficient alpha 1 is 10 to the power 2 per centimeter and alpha 2 is 10 to the power 4 per centimeter. After passing through a distance of 1 centimeter, which of the following statements is true about the light intensities I1x and I2x? So we have to choose the correct one. It's a very easy question. Basically, okay, so okay, so it's a very easy question. I is I naught exponential of minus alpha times x. Right? So if alpha is higher, I will be lower. Okay. So if everything else is same, I naught is same, x is 1 centimeter. So if alpha is increasing, I will decrease. Therefore, I1x will be greater than I2x. So it is option B. All right, let us take the next question. This is question 2. Please read the question and attempt it. Okay, so let us solve this question. The question says consider a gallium arsenide at temperature uh, 300 Kelvin. Assume the photon intensity at any particular point is this, and the wavelength lambda is this. The typical absorption coefficient of sunlight is this. This is alpha. For the steady state excess concentration per centimeter cube with excess minority carrier lifetime is this. This is tau. So we have to find the steady state excess minority carrier concentration, that is N. So N will be generation rate times the minority carrier lifetime, right? And generation rate G is given as alpha intensity times E, right? And E is 1.24 by lambda. This E needs to be in joule, right? This will be in electron volt. So lambda is 0.793. So if you substitute this, G is alpha is 20 to the power 4, IV is 0.05 by 1.24 by 0.793 into 1.6 into 10 to the power minus 19. What you get is 2 into 10 to the power 21. So this is the generation rate. This per centimeter cube second. Now N will be G tau, which is 2 into 10 to the power 21 into 10 to the power minus 7. So this will be, therefore the steady state concentration N will be 2 into 10 to the power 14 per centimeter cube. This is the final answer. This is option B. Okay, so let's take the next question. please attempt this question. Okay, so let's take a look at this question. The question says a single solar cell with maximum solar efficiency of 12.5, that means it is 0.125, produces a voltage of 1 volt and maximum current of 2 ampere. That means I use this, use this, I use this, and the solar insolation is 1000 watt per meter square. What could be the area of the solar cell in centimeter square? Okay, so theta is 0.125. The P out is Vi, which is 2 watt, and we know efficiency is P out by P in. So P in will be theta by P out. Sorry. So P in will be P out by theta. So this will be 2 watt by 0.125, which is 16 watt. Now the P in is insolation into area, right? So insolation is 1000 watt per meter square into area. So area will be P by P in by insolation, which is 16 watt by 1000 watt per meter square. So it will be 10 to the power 4 centimeter square, which is 160 centimeter square. Your area, which is this option C. Hello, let's take the next question. Please attempt this question. All right, let's take this question. A photograph has a responsivity of zero point 0.5 at 850 nanometer wavelength. Find the efficiency of the detector. So responsivity, sorry, just a minute. Okay, responsivity R is efficiency by E, which is eta lambda by 1.24. Okay, so efficiency will be R into 1.24 by lambda. R is 0.5 into 1.24. Lambda is 850. This lambda is in micrometer, so 0.85. Solve this, you will get 0.73. So efficiency is 73%. So this option. Okay, so this is the next question. Please attend this. All right, let's look at this question. The question says, consider the following statement and reason based on solar cells, current voltage, IV characteristics, and choose the correct option. Assertion: a solar cell must be operated in the fourth quadrant of the junction IV characteristics. Reason: in the fourth quadrant, solar cell absorbs electrical energy from the load to function effectively. So, which are true, or both are true, or both are wrong? So, if you see the solar cell's IV characteristics, it's something like this, right? This is ISC, this is VOC. So it operates in the fourth quadrant. Why it operates in the fourth quadrant? If you see VI is negative here. So it does not, when something is operating here, it is not consuming power. The power consumed is negative, which means power generated is positive. So to generate power, it needs to operate in this quadrant. So must be operated in the fourth quadrant. This is true. Assertion is true. Because solar cell absorbs electricity from load, this is false. Solar cell does not absorb any energy from the load. It gives energy to the load. It generates energy for the load. This is wrong. So assertion is true, and the reason, but the reason is false. Okay, so let's see the next one. Please attempt this question. All right, so let's take this question. Consider a silicon PN junction at T equal to 300 Kelvin with the parameters with the dopings of the P side and N side, the diffusion constants, tau n and tau p, the photocurrent density is B. This is the photocurrent density. Calculate the silicon PN junction solar cells open circuit voltage. So we have to find VOC, and we, VOC is given as KT by Q ln JL by J naught plus 1, right? And JL is given JL is 15 milliampere per centimeter square. J naught is equilibrium current of PN junction QNI square dN upon NALN plus dP upon NDLP, where ln equals to under root dN tau n, LP equals to under root dP tau p. So all these values are given. dN and dP are given, tau and tau p are given. That you can calculate ln and root p. D and dP are given. Na and ND are also given. Ni square, Ni you can take to be 10 to the 10 per centimeter cube. Q is 1.6 into 10 to the power 19. And so this J naught you will substitute here. JL is given. KT by Q will be 0.026. And this the VOC can be calculated. And then when you calculate VOC, it comes out to be 0.3. Okay, let's see the next one. Consider two silicon PIN diodes A and B with identical intrinsic region width of W is 20 micrometer. Assume the photon flux is 10 to the power 17 per centimeter square per second. Calculate the ratio of photocurrent densities in milliampere per centimeter square for photodiodes A and B. The absorption coefficients are alpha A is 10 to the power 3 per centimeter and alpha B is 10 to the power 2 per centimeter respectively. So find the ratio of photocurrent densities. So attempt this, then we'll solve this. Okay, so let's see this. So we know that J is proportional to flux into 1 minus e to power minus alpha times mu. So J by JB will be flux is same in both the case. So 1 minus e to power minus alpha A times width is also same, divided by 1 minus e to power minus alpha B times W. So it will be 1 minus e to power minus 2, 1 minus e to power minus 0.2. Is width is 20 micron and alpha is either 10 to the power 3 or 10 to the power 2. So if you solve this, it will be 4.8 J by JB. This is the answer. Okay, let's take the next one. Identify the correct diagram that illustrates the steady state photo-induced minority carrier concentration and photocurrents in a long reverse bias PN junction. The diagram shows PM0 and NP0, minority carrier concentration at equilibrium, JN1, AP1, minority carrier diffusion current densities, JL1, space charge region photocurrent, JL, the total photocurrent density. So we have to choose which one of these is the correct diagram. All right, to solve this question, we know NP junction, we have positive this side, and the depletion negative this side. So electrical will be positive to negative, like this. So this is wrong, and this is also wrong. Okay. And the second thing is when electron hole pairs are generated, so electron will go towards the positive side and holes will go towards the negative side, right? So current will be in the direction of holes or opposite to direction of electron. So this will be JL. So in this, it is opposite. So in this, all three are correct. So option A is correct. Very easy question. All right, let's see the last question for today. An avalanche photodiode has a quantum efficiency of 50% at a wavelength of 500 nanometer in the absence of multiplication, operated with a reverse bias to give a multiplication factor of 8. Calculate the responsivity in ampere per watt. Okay, so responsivity will be, we know, eta by E, right? And since we have a multiplication factor m also, so this is m eta into, let's C by lambda cube. So this is n is 8.5. Lambda in micrometer will be 0.5 divided by this is 1.24. This is the responsivity. You solve it, it comes out to be 1.61 ampere per watt at 1.6 volts. This option. Okay, so that's all for this week. We'll see you again on Monday for the week 12 live session. Then we'll have a summary session. Thank you everyone for joining.